Okay,
This is my one.
the last thing we talked about really was, the first isomorphism theorem. We did that in some amount of detail. Let me give you the following corollary. Whatever the number is, and this is a corollary that you've seen in the context of groups, and also in rings and ideals. Or the ring and B inside A are modules. Then there's a one-to-one correspondence. There is a one-to-one correspondence between our submodules. It writes pretty well, but it's squeaky. It's driving me crazy. And I don't want to give it up. It's writing well. Kind of this abusive relationship here. Between our modules A mod B and our submodules of A containing B. And I think, I'll go through this briefly. If you want more details, then don't be shy to ask. How does the correspondence work? Well, let me think this way. Submodules A mod B and submodules of A containing B. So let's suppose we have suppose C is a submodule of A that contains B. Then C corresponds to C mod B. Right. Just using the projection, right? You might think of this is projection from C to C mod B. Right? On the other hand, if X in A mod B is a submodule, suppose we have just some random submodule of A mod B, I know that X must be formed. Well, let me state it this way. Since X is a subgroup of A mod B, X is a form C mod B, where C is an abelian group that's nestled between A and B. back in the day when we did groups, we know that any subgroup of A mod B is of the form C mod B, where C is a subgroup of A containing B, right? So I'm really bootstrapping the group part. And C is a submodule. Since we're assuming X to be a submodule, and the multiplication on A mod B works the way it does, then C must be a submodule, right? Right, indeed, X we can realize is C mod B. And if R is in R, and C is in C, then R times C plus B equals RC plus B, which implies that RC is in C. So it's got the vacuum cleaner thing going for it, right? So if you do this correspondence here, if you start with C and go to C mod B, make your C mod B X, then this correspondence gets you back to C, right? Here C is the subject of the correspondence here. And if you start with C mod B here, or if you start with this X, which is C mod B here, then when you do the correspondence twice, you get C mod B. So is that clear enough, or do you want me to dig deeper into this? Yes.
So C is a submodule because the way X is defined?
That's right, because I'm assuming X is a submodule,
Mhm.
right? I mean, right here in this part of it, I'm saying, well, it's a subgroup. I'm not using any of this. But once I know it's of this form, I know that this thing is a submodule. And this computation here shows that C mod B is a submodule of A mod B. And this computation shows that indeed C is a submodule of B.
Okay.
Right. I'm sorry, is a submodule of A. Okay. Other questions? Okay, so now we're going to take a little bit, we're going to study on the notions of direct product and direct sum. So somebody tell me from the old days in 4120, or wherever your travels have taken you before this, if I have, let's say, a bunch of abelian groups, right? Can somebody describe, so this is going to warm up here. Uh, um, suppose um, suppose I have just this collection of abelian groups, AI. Okay. Can anybody describe what the direct product and the direct sum is? So if I
like you're making tuples basically.
that's essentially it. This is just the collection of AI. I agree with that. So, for example, if the set was finite, it would just be in tuples, right? A1, A2, it'd be like the Cartesian product you're used to, right? And if this is a countable set, you might think of this as a sequence. I think of this more generally as a net, right? Because my index set might even be an uncountable. This might be just disgustingly huge. But it's all the same principle. Whether I've got two coordinates or uncountably many, it's the same distance, right? I agree. And my addition went something like this. So what was the sum of these two things? How did we get it to barf out a new sequence?
Plus PI.
Yeah, that's right. You added up sort of loosely speaking coordinate wise, because that's the easiest thing to do. Right? And of course, this all makes sense because each separate AI is a group, so the separate sums make sense. Notice that, of course, the zero element is the string of all zeros. Everybody agree with that? And of course, everything has a minus sign, just reverse the sign of everything in here, right? So this is all good to go. Do you remember the distinction here with the direct sum? Direct sum is a piece of the direct product. Do you remember what the restriction is? What,
Only finitely many are non-zero.
right, some people in algebra, remember the theory might say, have you all heard about almost everywhere in advanced calculus, right? When somebody in algebra number theory says almost everywhere, that means AI equals zero, except for at most finitely many. Right? So in other words, this is the subset of the direct product. In direct product, you got complete freedom. You can stick whatever you want in any coordinate. You're all good to go. The direct sum is all of your coordinates have to be zero, except for finitely many, right? Finitely many, you can add non-zero entries. When I first saw this, when I was an undergraduate, I was like, what the heck is this? Somebody made up some crap so that they could have homework exercises, right? That's what's going on here. But surprisingly enough, I think this one is fundamentally important, and we're going to see why. I mean, well, why do we want zeros on the server? What's special about this, right? Why is this so important? But it turns out that, okay, so here's I love doing spoilers, I guess. Suppose I have an arbitrary R module M, right? Any R module you want. It is the homomorphic image of a direct sum of some number of copies of R, period. So you just take R, you take the direct sum of R over maybe a big index set. That module M will be a homomorphic image of this. So these are kind of these are kind of the daddy mac, if you will, of R modules. So direct sum is actually quite important, right? And we'll talk about some distinctions here. This one kind of has more freedom to it. How many of you have seen, maybe not quite as general as this, but how many of you have seen, oh, but let me make one other point. Let me also point out that if the index set is finite, right? So if I is finite, then there's no distinction here, right? Because if there's only finitely many entries, you've got complete freedom, right? Yes.
So since like only like a certain amount can be zero, like so is the direct sum never zero?
No, the direct sum, it has the same zero as the direct product. You can fill it up with zeros if you want.
Oh, okay.
Your only restriction is you can only put in finitely many non-zero entries for any
Oh,
element.
non-zero. Okay.
Yeah, only finitely many non-zero. Okay, other questions? But actually, this definition, which even if you have my 4120 card, is actually a little bit incomplete. The direct sum and the direct product are not just these structures. There are also these structures that are equipped with homomorphisms, right? And I will try to make that clear here. Theorem. Let's let AI be a family of R modules. Modules. And the direct product, AI, and direct sum. The direct product and direct sum of the family. As abelian groups. So once again, my old familiar appeal to abelian groups. Then the direct product is an R module. Right. Number one. The direct product of AI is an R module with action given by R times AI so I think it's what you would think might come naturally. R times one of these generalized sequences. Well, you just slide the R in. There you go. The direct sum of AI is an R module with inherited action that is, it's the same action that I get here, because remember, this is actually a subgroup of this. Here's the part that often in the beginning is kind of left out. For all K in the index set, right, the canonical projection we'll call it pi K. Given by what's the most sort of natural way that you can think about this map working? So you pick a K out of the index set. So that corresponds to this AK over here. That's the target of this homomorphism. if I input one of these sort of generalized sequences, what's the easiest way that you can think that pi k acts on that?
Spit out AK.
Just, it reads the kth coordinate and spits it out, right? That's a good way to put it, right? But does everybody see how this works? It just reads the kth coordinate. Hey, who are you kth coordinate? There you go. And that gives you something AK. Yes.
Is it just giving you like that one coordinate, or is it like the sum up to like I?
No, just a single coordinate, because remember, a good thing to keep in mind is there might be no apples and oranges in here. All these AIs may be different, completely different structures, right? But they're all R modules. And so an element of A1 plus an element of A2, it may not make any sense to add them up at all because they're different modules, right? This is an R module epimorphism. This one's a little bit harder to wrap your head around, this one, the one for the direct sum. For each K, out of K, this goes from AK into the direct sum. This one's a little bit, I think the direct product's a little bit easier to kind of wrap your head around what should happen. What do you want to go from the direct product of all these things into one of the components. Just read what's in that component's coordinate, just that's your output. Now I'm trying to go the other way. I'm trying to take an input iota K takes A sub K, and this is now going to be something in the direct sum. How do I do that? That's a little less clear, I think.
Set everything else to 0.
And there you go. So here's what I know for sure. I know it's got to barf out some generalized sequence. So it's got to be something like this. No matter what, my input is from here, so my output has to be a generalized sequence, right? Now I'm gonna tell you how to define the x's. Xi is equal to AK if I equals K, and 0 if I is not K. So that's exactly what was prescribed. The easiest way to make something in the direct sum is put your offending AK in that coordinate and put 0 everywhere else, right? This is an R module monomorphism. Everybody okay with that? So, really speaking, from those of you that have an interest maybe in this kind of thing, if you like abstract nonsense, category theory, things like this, really what the direct sum is it's not just the direct sum of this family of modules is really, direct sum, I'll say first, it's really the collection of this structure right here, equipped with all these injections, right? So it's really not just the direct sum and I play around with it, make a module. It's the direct sum coupled with all these homomorphisms that go from the pieces of the direct sum into the whole direct sum. The direct product technically is not just this direct product piece, but it's also these projections that project onto the pieces of the direct product. And we're going to see that the direct product and the direct sum are what we call universal constructions. In other words, they're the only way to make these modules that have certain mapping properties. Sometimes you wonder if, a natural question in mathematics might be, and this is just one of many kind of questions. Suppose I have a homomorphism. This could be a billion groups or modules or whatever. And suppose that well, let's see. Okay, so this is a good example too. And suppose I have a surjective homomorphism from here to here. And suppose I have a homomorphism from here to here. Right? Under what circumstances do I have a homomorphism from here to here? Or what about in the other direction, right? And so you could ask these kind of questions, right? If I have a homomorphism from the group A to the group B, does this extend to a homomorphism in an intelligent way to a larger group or something like this? So there are lots of good questions that you can answer like this. And so we're going to see that the direct product and the direct sum, in a certain sense, are what we call universal objects with regard to certain mapping questions that you might have. And in fact, well, let me thought my way through this, because I did say theorem, didn't I? Let me ask you this. How many of you all are convinced that we already know that both of these animals are abelian groups, right? And in fact, we even talked our way through that a little bit. Are you convinced that this actually makes it an R module? Is everybody comfortable with that? How about, let's sketch a proof of 4, right? I think, I'll leave 3 as an exercise, because I think it's not too difficult to show. Okay, let's let AK into the direct sum be given by I over K of AK is when XI equal AK and 0. Okay, well, let's see, what burden do I have here? I need to show that this is an R module monomorphism, right? Well, let's look at AK plus R AK prime. Okay. Let's see what this gives us. This gives us, by our rule, where XI equals whatever this crap is, AK plus an R AK prime, I equals K, 0 else. So notice that I guess I probably should have started from this point if I had been smarter about it, but of course I wasn't. With I equal to AK, 0 else, and I A R right. this is equal to, R ZI. Where ZI is equal to AK prime. If I equals K and zero else. So this in fact is equal to, and of course, RZI is equal to ZAK prime, not Z, RAK prime. If I equals K and zero else. Yeah. And so if we put this all together. There we go. If you piece this together by putting the sequences together. YI plus ZI actually gives you this, right? Everybody okay with? So that means that it's an R module homomorphism. Need to show it's 1-to-1, right? For 1-to-oneness. Let's suppose. Let's go up a little. Suppose. AK is in the kernel of iota K. So iota K, AK is equal to with XI equal AK 0. But if this equals 0, this implies that AK equals 0, so iota K is 1-to-1. So it's an R module homomorphism, the kernel is 0, so it's 1-to-1. So we have it's an R module monomorphism. Okay, any questions on that? Questions?
So if that equals 0, the inside element, the element you're plugging in.
Right,
Equals
so
0.
this means that, right, so this is 0 by assumption that it's in kernel. But since this is 0, that means that this has to be 0 in every coordinate, including this one, so AK has to be 0. Questions? Okay, so let me give you. Actually, I'm gonna do this in parallel. I'm gonna do these both at once. Well, in tandem, I've got them. I'll try to prove the price somewhat, because it's more fun. I'm gonna do this. This kind of illustrates sort of the dual nature of these results. So I'm gonna put these theorems down. Theorem 1232. And in parallel, so I hope you all can kind of see the comparison here. The other theorem. Or some ridiculous other number. Little one. 1233, so not that ridiculous. This will be the universal mapping property for the direct product, the universal mapping property for direct sum. Let's do, the product first. I'll assume that the ring is, commutative ring one. But R is a commutative ring one. And let's say that, AI is a family of R modules. And C is another R module. And I've got a collection of homomorphisms. This is a family of R module homomorphisms. When I first saw this theorem many moons ago, I was like, this seems like really contrived, right? Because, I mean, the first thing that bothered me was, okay, I've got this collection of R modules, I can buy that. And I've got another module, C, I can buy that. But then I've got all these homomorphisms from C to AI. It's like, how do you know? But rest easy, young minions, because, this, I always thought, well, what if there's, no homomorphism? But of course, there's always a homomorphism from C to any AI. Because if nothing else, you could take it to be the zero homomorphism. Nobody said this had to be anything fancy, right? Some of these could be the zero homomorphism. All of them could be, right? Then there is a unique R module homomorphism. Then there exists a unique R module homomorphism. Capital Phi that goes from C to the direct product of AI. This satisfies this Kalman property, such that pi I capital Phi there goes this, right? So I like to draw this diagram this way. So what you have is you have C. And what do we have here? We have we'll call this P sub K. Into the direct product. Oh, yeah, this is just the one that goes to a K. It's like the lowercase p goes into AK. You have the direct product here. Now, do you remember that we have the projection, right? So for every one of these, we have a projection, which I call pi k. So what this says is for every diagram like this, as you run through all the indices k in here, there is a unique homomorphism capital P, it makes the diagram fit. That is, for every K in this index set, if you input C and you go here, it's the same thing as projecting here and then projecting here. And the direct product of AI is determined uniquely. Up to isomorphism. As its property. And what I mean by that is, if I come up to you on the street and I say, I've got this R module, and this R module is so cool. This R module has these projection maps onto these modules. And so if I have any family of homomorphisms from here to here, then I can find a unique homomorphism from here into my mystery module that makes this diagram commute. Then what you have is the direct product, period. That's it. Up to isomorphism, this is the only solution to this problem that works for every K in the index set. Alright? So it's unique in that regard. There is a dual notion for direct sum. So the theorem starts out about the same. R, commutative ring of 1. And here, I'm gonna keep my notation here. Okay, I do D here. AI, a family of R modulus. And, well, D, an R module. And here we have another family of homomorphisms. I'm gonna call these pitchfork. And they go from A, D, a family of R module homomorphism. So the setup looks almost the same, except for what? What's different about the setup here? The direction of the family of R module homomorphisms. Before I had everything, from my random module C, I had everything pushing to the AIs. Now I've got all the AIs pushing to this module D. In this case, there is a unique R module homomorphism. There exists a unique R module homomorphism. I'll call it capital P4. It goes from the direct sum of AI to D. Such that pitchfork, capital pitchfork, iota K is piece of K for all K in the index set. And I'm going to draw a diagram again. Same perspective, right? D. This time, all the A, each AK goes here. This is iota K. Oh, it's not iota K, I'm sorry, it's pitchfork K. There we go. You also have the direct sum of AI. And you have all these, remember these little canonical injections here. See the difference in the diagram there? It's a mirror image, right? All the errors are reversed. People started realizing that you could do lots and lots of things with category theory, lots of theorems just by, oh, I've got a theorem, so now I'm gonna turn the arrow around. People made a living off of this in the sixties, right? But this is like a really cool result. This is the mirror image of this. The arrows all going the other way. Direct sum projects onto, right? And on the other hand, you have something inside the direct product. I'm using that loosely. This may not be one to one, right? And actually, this is kind of the cool one in a certain sense. And we're gonna see later, actually, that this is why every R module we're gonna see is a homomorphic image for free module. That's gonna be a consequence of that. Let me give you the final statement on this, and this is, again, the direct sum, just like the direct product, is uniquely determined. Up to isomorphism. By this property. So it's the unique solution to this mapping problem. It's a universal solution. Okay, any questions on this? This is a really fun proof for this. And I'm not gonna prove it until next time, but I will give you something that I think might be useful for you computationally coming up. So I'm gonna give you this, any questions on this before this is something that you've seen for sure, I think. For sure, I think that doesn't control it very well, does it? This is something that well, anyway, so if you haven't seen it, you're gonna see it now. So proposition 12.3.4. Let R be a ring and you have a family of R submodules of A. Again. And AI, a family of R submodules. So A is just some R module, and these animals are just R submodules of it. Such that number one, A is the sum of a family of modules. And remember, what I mean by this is, if you just take everything in all those AIs and dump them all in a big trash heap and see what they generate, it will be all of A. So if you take all the elements of all the AIs and put them together, you get all of A. And two, for all K and I, index set, AK intersect AK bar is 0, where AK bar is the sum of all modules. So it's everything that's generated by everything that's not that particular AK. Then A is isomorphic to the direct sum of AI. So this is something you've probably seen before. For example, when you had a billion groups, if you had two groups and when you put them together, they generated the whole group. And if the intersection of them was trivial, then that meant that it was the direct product of those two. Any questions on that? We'll prove one of these, next time and get on to this, any questions? And we'll see you on Friday.